So hello students, welcome back to our video classes, and I'm Anik Ghosh, your chemistry teacher, and this is our second last video on metals and non-metals. I think you have gone through the other videos. I think I don't have to say it in all these videos, right? You know that what is the importance of this chapter, and you cannot just take it from the middle. As for that reason, you need to go from the very first video. So if you have seen my all the previous videos, then definitely you are going to understand it very well. So today we are going to start with the extractions of metal from its ore. So from our previous discussions, I think you know that the metals are being drawn out from the ores, okay? And you know the difference between an ore and a mineral, right? Now, the ore here from the ore, so in the ore there are so many things which is which is there. And in the last video we have discussed about the concentration of ores by the physical methods, okay? And today we are going to, after getting that thing, after getting the pure ore, whatever it is, if it is hematite for iron or bauxite for aluminium, whatever it is, zincite for zinc, copper pyrites is for copper, so you know all about it. So whatever it is, when we are just have the concentrated ore in our hands, now our work is to extract the metal out of it, okay? As you know, in the ore the metal remains in oxide forms like Fe2O3, hematite, in oxide form, or in carbonate form like calamine, zinc, okay, or in like sulfide form, okay. So there are so many ores which is there in sulfide form as well, galena, okay, or cinnabar, okay. So these are the like, or bauxite as well, that is another oxide ore, okay, oxygen or oxide ores. So many, there are so many ores where you can see they are in different forms, they are in different forms of this forms of oxides or carbonates or sulfides, those things, right? Now from here, how would you get this particular this metal? Like from here the aluminium, from here the iron, okay, how would you get them from here? So that is the thing that we are going to learn in today's video. Now for low reactive, high reactive, and intermediate, so we are going to separate the all the metals in three forms, okay? One is for the low reactive, another is for the high reactive, another is for the intermediate reactive. So for these three types of metals, what would be the processes through which we are going to extract them, okay? Now another thing is reduction of ores. So after extracting them, we have to reduce it, because in the when we are going to in order to extract them, because in most of the cases we are going to extract them in the form of some oxides or from that thing, so we are going to learn about that. After that we have to reduce them to get the particular ore, okay? That reduction can be done via usage of coke or those type of things, or maybe some stronger reducing agents like aluminium, okay? And there is another process which is for electrolysis. So we are going to read all of those things in today's class. Now the first thing is extractions of metals from its ore. This is the first process. So the extraction of metal from its ore is from its concentrated ore. And now you know how to concentrate an ore, right? We have learned about magnetic separation. I think you remember physical processes. That was the that was one of them. There were Froth-floatation as well. So these are the processes. This was a gravity separation process, Froth-floatation, right? So these type of things are there, or is essentially a process of reduction of metal compounds in the presence of its ore. Okay. Now they're saying that like concentrated ore is essentially a process of extraction of metal from its concentrated ore is essentially a process of reduction of the metal compound present in the ore. Okay. So this is nothing but a reduction process. Okay. Now we are going to go through the reduction process, how we are going to take out the metals from its ore. So first is, so as I told you, we are going to categorize in three ways, right? In three ways. One is for the highly reactive elements, highly reactive metals, okay? The second is for the moderately reactive metals. And a third one is for the low reactive metals, okay? Now, we would start the class with the highly reactive metals. The highly reactive metals such as potassium, sodium, and calcium, and you know about them. If you have gone through the metal activity series, you know that potassium, sodium, calcium, they are the top three reactive elements, right? So, uh, if you just want to separate them out, magnesium and aluminium are placed high up in the reactivity series, and if you just want to take them out, you have to do it via reduction of their oxides. Metals cannot be, yeah, we have to do it via electrolysis. Via electrolysis, because they are very reactive. Okay, and you cannot separate them out with the help of reduction processes. Look, if that was something like zinc oxide, which is moderately reactive, then we could have used this carbon or coke. And you know that coke is a very good reducing agent. If I just mix some coke with it, what would happen? It would give you carbon monoxide plus zinc, isn't it? That was very simple. This process is very simple. Now, this is for the moderately reactive elements. For the highly reactive elements, you cannot separate them out in this process. So what you have to do is you have to do electrolysis. Let's see. Here you can see the potassium, sodium, and calcium, how they are in the top position up to aluminium. So all these elements are very, reactive elements. So you have to use electrolysis method. Okay. Now, for the elements, those are in the, like, they are the moderately reactive, like zinc, iron, and lead. For them, you have to use the carbon in furnace. So for potassium, sodium, calcium, and aluminium as well. Among them, the most important extraction method is for aluminium. We are going to learn about the extraction method of aluminium separately in this video only. And for potassium, sodium, and calcium, we are just going to use a salt of that, like Na comes as rock salt, which is NaCl, right? Which is NaCl. Now we are just going to take it for electrolytic reduction. I'm not teaching you, I'm just giving you the overview. And we are just going to take that NaCl, molten NaCl, in the beaker. Now you get it, I guess, what I'm going to do. So after that, if I just turn the switch on, what would happen? It would break down in Na plus and Cl minus, right? It would break down in Na plus and Cl minus. And from there, I think you can understand, we would reduce this sodium, we would reduce it to get sodium metal. So this process is a very simple process, as you can see. The same thing is done for potassium and calcium and aluminium as well. But for aluminium, this process is a little bit modified, because for aluminium there are so many problems, because you have to see, like here I am using molten NaCl, but for aluminium to melt it, we need a very high temperature, like near about 2030, okay, degree centigrade. Okay, I might be a little bit up and down, but it can be. So the thing is near about 2000. Okay, so this is the boiling point of aluminium, melting point of aluminium. So to use molten aluminium, it's very difficult, right? Now, definitely we are going to read about that, then how to do the extraction method for aluminium. So first thing is extraction of sodium metal. Okay, how extraction is done for sodium metal. Sodium is extracted by electrolytic reduction. As I told you, for the element, those are very reactive, like sodium. It's a very reactive, like highly reactive. For them, we cannot use any reduction processes other than the electrolytic reduction of molten sodium chloride. So we need to melt it. And if we do not use this molten sodium chloride, if we just use some aqueous NaCl, then this process would not occur. Because if you use aqueous NaCl, think about it. What would be the product? If you use aqueous NaCl, what would be the product? In aqueous NaCl, there are NaCl and there are water, right? NaCl and water. So there would be a competition, right? There would be two cations and there would be two anions as well. And the thing is, in this competition, like in between these two anions and these two cations, what happens is H plus have higher tendency to go to the electron. So instead of getting sodium, we are going to get hydrogen in one electron. And in the other one, we are going to get oxygen, because OH minus has greater tendency to get released in the electron rather than this Cl minus. So if you use aqueous NaCl, this reaction won't work. We need to use molten NaCl. Clear? Now, on passing electricity with highly molten sodium chloride, decomposition occurs and sodium metal and chlorine gas are formed. Molten sodium chloride contains sodium and chloride ions. So let's see what are they trying to tell you. Let's say this is a carbon electrode, okay? Graphite electrode. Fine. Now I am just connecting it with a battery. Okay. So definitely this electrode gets plus charge, this electrode gets minus charge. Now I'm going to put some NaCl. Never mind the color. Okay. So color is going to be colorless, right? So I'm putting some molten NaCl over here. So I think you know what do they mean by the word molten? They're just melting the NaCl down. So when the electricity starts, when the key is on, what happens is NaCl would break into Na plus Cl minus, isn't it? NaCl would break into Na plus Cl minus. Now this Na plus would go towards this electrode, okay, and this electrode is known as cathode. Where cation goes is called cathode, and the Cl minus would go towards the anode. Where anion goes is called the anode. Okay. Now, when after NaCl, Na plus goes towards the cathode, you can see in the cathode there are so many electrons because the cathode is negative. From there, I think you can understand the cathode has a huge amount of electron in it. So it would take the electron from there. So this process is the reduction process. This happens in the cathode. Okay. It takes up the electron from there to give you sodium metal. Okay. So that is how you are going to get sodium metal over here. And in this electron, in the anode, you are going to get Cl minus. Cl minus goes in the anode, and you can see the anode is lacking of electron. That's why it is positive, right? So what would happen is it would release the electron there to give you chlorine. Now, if I just balance it, 2 electron to give you Cl2 gas. Okay. So, and here it is sodium solid. So in the cathode, sodium gets deposited, and in the anode, chlorine gas gets evolved. So you'd get some bubbles of chlorine in this electron. Okay. So these are the bubbles of chlorine. So that's how you can take out sodium from the electrolysis methods. Okay. Let me tell you, in this method, if you take out a particular metal, it is near about 99% pure. It is near about 99% pure. So I think you can understand this process is a very useful process. And let me tell you, whether it is a reactive metal or not, at the end, to purify a metal, we always use this method, this purification method. So this method is very useful method. So try to understand this thing. This is very simple as well, but yet it is very useful. Okay. If you want to get a very pure metal or anything like that, then this is the process you have to do. Okay. For getting pure substances. Okay. So in the extraction process of any metal, in the end, you are going to purify the metal. Like in the most of the cases, the metals you are going to get is near about 60 to 70% pure. Okay, to make it over 90% pure, you have to do this like electrolysis for all of them. Now we are going to start with the extraction of aluminium metal. As I told you, sodium, potassium, calcium, all of them can be separated out by that method only. Aluminium is also very reactive, but for aluminium we have to make a new arrangement, because as I told you, aluminium comes from bauxite or alumina. Okay, now this bauxite, to melt this, you would not be able to do that because you need it molten state, isn't it? But as I told you, to melt it, you need 2000 degrees centigrade. Sorry, 200 degrees centigrade. Let me think. 2030, isn't it? 2000 degrees centigrade, which is a very high value. But you can do one thing. If you use some cryolite and another substance is called fluorspar, cryolite and some fluorspar with this alumina, what would happen is this value comes down. The formula of cryolite is Na3AlF6 and the formula of fluorspar is CaF2. Now what happens is it would take the temperature down from 2000 degree down to 900 degree. So now you can see attaining 900 degree is simple, is easier. Look, the thing is, like this is the melting point of alumina, but the melting point of aluminium metal is not more than 660 degrees centigrade. Now think about it. If I melt it down, even if I just get succeeded to melt it down, and if I just still get succeeded to reach up to this temperature, if I just melt it down, at the end, what would happen? At the end, the thing that is having 660 degrees centigrade as melting point, it is in 200 degrees centigrade. So it would get ruined, right? Isn't it? It would get ruined. So for that reason, if I just take it down to 900 degrees centigrade, so this is a win-win situation, isn't it? So 660 degree can hold up to 900 degrees, and you can also attain a low, like a relatively low melting point for that. So for that reason only, we use this cryolite and fluorspar, these two things for alumina, and rest of the things are just the same, Okay, this is where I put Al2O3. Right, this is what I put Al2O3. Now what would happen? So look, there is another problem that most of the student faces. You might be thinking, here also very good competition getting generated, isn't it? Like, look, what are the competitions over here? Na plus coming from cryolite, right? And Ca2 plus coming from fluorspar. Along with these two, you are getting Al3 plus. Now, definitely there is a competition that who would go towards the cathode. Cathode is negatively charged, so everyone wants to go towards the cathode. But who would go in between these three, among these three? What happens is the element which is less reactive, which lives down in the group, has a more tendency to get reduced in the electron. So the element, the metal, which stays down to the group, okay, which is less reactive, has more tendency to get released at the electrons. So what would happen is aluminium would go, although there is a competition. So using cryolites and fluorspar is not a bad idea, right? So it would take the 3 electrons from there to give you aluminium metal, which is again going to be near about 99% pure. But the thing is, you are going to get this aluminium metal in molten state. Okay, in molten state. So that is how you are going to take out this aluminium out of this ore. Okay, hematite. So that was a very good process where we have so many things to understand. So it increases, like, usage of cryolites and fluorspar. If someone asks you, you would be saying that it is decreasing the melting point. And there is another thing it is doing. It is increasing the mobility. It is increasing the mobility of the reaction. Okay. So that's it. That's all about it. All about the aluminum metal extraction. Okay. So let's just see what happened. So we used Al2O3. Along with that, we used Na2AlF6, Na3AlF6. Let me see. Yeah, here it's right. Na3AlF6 and CF2. These three things, like Al2O3, Na3AlF6, and CF2. And we are getting Al and oxygen out of it. So what is the cathode reaction? The cathode reaction is going to be Al3 plus takes up 3 electrons to give you aluminium, but in liquid state, right? In molten state. And in the anode, okay, in the anode, what are the competitors? That is F minus, and there is OH minus, right? No, let me see. No, there is O2 minus, right? So these two are the competitors. So this is O2 minus has more tendency to go towards the anode. So what would happen is O2 minus would just lose 2 electrons. Like 2O2 minus would leave with just 4 electrons. Okay, just wait for a moment. Sorry. Oh, I just, yeah, got it. Thank God, everything is there, I guess. No, it's not. Just give me a moment. Oh. So everything's gone. I have to write it all over again. Yeah, so what was I writing, like over here? So if I just want to extract alumina, I need to use Na3AlF6. Along with that, I used to use the cryolite and the fluorspar. This is the fluorspar. And from there, if I do the electrolytic reduction like this, I'm going to get aluminium at the cathode and oxygen at the end. So what is the cathode reaction? The cathode reaction, and the other one is the anode reaction, right? So as I told you, in the cathode, it is going to be like, Al3 plus is taking 3 electrons to give you aluminium, right? And the anode is going to be like O2 minus, 2O2 minus is leaving 4 electrons, okay, leaving 4 electrons to give you oxygen gas. Okay, so this is the entire reaction. So I have written over here, the competition was in between OH minus and O2 minus. Sorry, F minus and O2 minus. Okay, so O2 minus would then definitely win in this. So this is how you are going to do it. So this is the solution of bauxite and in cryolite. So this is the solution of Al2O3 in Na3AlF6. This is cryolite. Okay, that is fluorspar, CF2. So you would get this, right? Now, I think you have understood about how to separate out the reactive ones. Now you are going to go through the moderately reactive ones. Now to separate out the moderately reactive metals, which are in the middle of the reactivity series, are extracted by reduction of their oxides with carbons, aluminium, sodium, or calcium. So what happens is, for the low reactivity ones, as I showed you earlier, they just use coke in it, and you'd get, okay, they just use coke in it, and you would get CO and Zn, like the reduced product, okay, the metal. So this process is called carbon reduction. So let's watch a video over here to understand what is this extraction of metals methods and all. Okay, this is Hindi, so I'm going to translate the entire thing to you. Just give me a moment. I think you'll not be able to see it, right? Just give me a moment. Just let me make it all right. Yeah, so I fixed everything, so I think you'll be able to see it now. Just give me a moment. Yeah, so it would take some time to turn it, like, to get started. So until then, I'm just going to tell you, okay, it's done. Yeah. So as you can see, this is the entire flow chart through which the concentration of, and after that, what are the processes you are going to do. So you can see the metals for the over here. You can see over here, for the metals of medium reactivity, what are we going to do? For the metals of low reactivity, what are we going to do? And for the metals of high reactivity. So for the high reactivity, we are just going to reduce it. Okay. And for the medium reactivity, we are going to perform these methods. Okay. The methods you can see: carbonate ore or sulfide ore, they have calcination, they have roasting, and those methods. Okay. So carbon reduction. So as you know, carbon is a very good reducing agent. So that is how it can do that. Sodium oxide or magnesium oxide, if you just sodium, okay, those things are, these things cannot be separated out, right? We need to make it like electrolytic reduction, because they are very much strong metals, right? And you know why we call it reduction? Because in the cathode, ultimately what happens is the reduction, right? Reduction of metals. So sodium chloride, potassium chloride, for everyone. Now just go through the electrolysis process. As you know, in the electrolysis, there are two electrodes, there is a battery, there is a switch, and there's a container, which is called voltmeter. So that is what NaCl solution is. When you switch it on, what would happen is, you know it already. Sodium and chlorine are going to get separated out, and solid NaCl. Okay, they're saying that solid NaCl is an insulator, because you know that if you want to get ions, you have to dissolve it in water, right? Otherwise, they would not be able to, if they are not ions, they would not be able to do that, right? Liquid NaCl is a conductor, right? So sodium and chloride, so they are going to get divided into that. Now the electricity is there. That is anode and that is cathode, as I told you earlier as well. So you can see, like, all the positive charges are going to go towards the cathode, and the negative charges goes towards the anode, right? The positive charges over here is the sodium, right? and the negative charges are the oxygen. Okay, this is molten sodium chloride, so it would be sodium and chlorine. So this part is the reduction. You can see this is what happens in cathode. For that reason, we call it electrolytic reduction. Right? The same thing happens for chlorine as well. Okay, so this was the thing about the previous one, and for now, the moderately reactive one, the first thing is what you have to do is through some processes, you have to, whatever the ore is, you have to take it to oxide. Like zinc comes in sulfide or carbonate, right? So they have their own ways to for zinc sulfide and zinc carbonate. What happens for them? The thing is like for these elements, you need to perform calcination and roasting to get into these oxides. After you get oxides, from there, getting the zinc back is not a difficult part, right? Through the reduction through the carbon only. Now, let's understand what is calcination. When you have a carbonate ore, the work is very simple. Just heat it. You know what happens when you heat a carbonate or a bicarbonate, right? You know it. Because when you heat a carbonate or bicarbonate, it gives you carbon dioxide. But how do you know? Because you know that in our kitchen there is baking soda. If you heat it, you are going to get Na2O, CO2. Sorry, wait for a moment. Yeah, NH2O. Okay. And same happens for carbon. So for all the carbonates and the bicarbonates, all of them breaks into carbon dioxide, right? So when you just heat it, they would break into carbon dioxide. And apart from that, what is left? ZNO. So ZNO plus carbon dioxide. This is what they're going to get over here, right? Now that was our target, right? After that, we just reduce it with carbon, and we would get our zinc back. Okay, this is the one thing we can do. And the other thing is, so this is, you can see all they are writing calcination is a process of heating ore in the absence of air. So all this thing is in the absence of air. Okay. Okay, in the absence of air. So this thing is called calcination. Okay. Now what is called roasting? So roasting is exactly what you are thinking about it. So just like roasted foods, this is roasted metals. What happens is when you have heating of lower melting point, so what happens for is like if something is there as sulfides, okay, something is there as sulfides like zinc sulfide. Now roasting is burning in presence of oxygen. Okay, so not like the last one, not like the burning in a inert atmosphere. It's like burning in front of oxygen. So you'd get ZNO. Now from ZNO you can work, right? From ZNO you can work. Now, extraction of lower reactivity methods. Before going to that, let's watch a video on roasting and calcination. So as you can see, extraction of less reactive metals, all of them are below hydrogens, right? In the periodic table, in the like metal activity series. So that is how you can take out the oxygen and you can get the metal back. So the thing is to get oxide. If you get oxide, the work is very simple for you. Or either you heat it or you give it some reduction. Okay. That is the thing they are saying. Heat it with presence of oxygen. Okay. You can see over there as well. So this is the same thing we are trying to teach you over here as well. Now, for the low reactive metals, for silver, gold, platinum, and platinum are metals with very least reactivity. They are found in nature. Low reactive metals are extracted by reduction of carbon. Okay. Now I think like that was all about it. That was all about the entire video. Now we are on the verge of completing this video. So now this is the FAQ, frequently asked question, where you can see what are the methods of extracting the metals. So the answer is there are three main methods. One is extraction, they are reduction of ore with carbon, reduction of the metals ore by electrolysis, and ion reduction of the ore. These three processes over here, like they are the reason, they are the main reason behind this. Like this is the how, not the reason. So this is how you can extract the metals. So there are three main methods. What I mean to say is it's method. Okay, so that's it. I guess you have understood entirely. Okay, this was a very simple class, and you just go through your modules now. Okay, we are about to end this chapter as well in the next video. Keep on watching them and keep on learning from Ask IITians. And one more thing I forgot to tell you, like if you have any doubt, you are going to just write it on your phone. Okay, for bye for now. We are going to meet each other in the next video. Okay, bye everyone.